Testing, testing, testing. Testing, testing. 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 Testing, testing, testing. Let's test it out. Looking good. Alrighty. Happy Wednesday, people. We're taking a little break from the code. And we're doing a quick paper read. So today we're going to be reading a paper about robotics, specifically reinforcement learning, and specifically the combination. So deep reinforcement learning applied to robotics. So this is a field that I've kind of worked in, and I feel like it's a little underrated. You know, obviously the technology is not quite there yet, but this demo was super impressive, and it's a big DeepMind paper with a lot of names on it, so I think it's worth exploring. So let's look at this. We got 26th of April, 2023, so relatively recent paper here. We got DeepMind. We got University of Oxford, and we got Google. So Google is DeepMind. Google and DeepMind are basically the same thing. When I was working there, the teams were actually separate. So you had Google Brain as a separate team, and then you had the DeepMind team was a separate team. But now, I think very recently, they actually just combined them. So likely what happened is, I don't know if this team exists anymore. What probably happened is that there was a team at DeepMind working specifically on this, and then once they combined the DeepMind team with the Google Brain team, they said, okay, everybody close out whatever you're doing, whatever research you're doing, make sure it comes to a nice ending, publish your paper, and then we're going to take everyone and have them work on a chatbot. So that would be my guess, is that this is not going to be a thread of research that they continue to pursue. It's going to be kind of the final culminating moment of the work that they did. And I suspect that many of these people will go work on RLHF, reinforcement learning from human feedback, with a chatbot. But the stuff I saw here was really, really cool. So they had these little humanoid robots, right? And the little humanoid robots played each other, right? And you can see them, look at them. They're fighting. Look at that. They're trying to play. They're actually really good at getting up. And one thing I immediately noticed is the arms. You see how they're kind of like, they have their little arms out like that? It's actually a really good way to balance yourselves. You see how they're kind of constantly moving their arms around to balance their little bodies. And another thing to notice here is that there's a fundamental difference between this type of robot you see here and the Boston Dynamics robot. The Boston Dynamics robot is executing a very, very precise control strategy. It's what's called optimal control, right? And that's the type of control strategy that has existed for a very, very long time. And basically the idea is, hey, we know Newton's laws of physics. We know the mass of every single part in this robot. Let's calculate the exact position of every single joint such that we have a very specific motion, right? And if you actually look at the YouTube Boston Dynamics robots, they're very elegant and smooth in their motion. You see how look at the feet, look how stable the feet are, look how stable the body is. You see how the camera is almost stationary. It's like tracking its head, right? Versus if you look at this little robot here, you see how much it moves, how much it wiggles? That's because it's not executing any kind of optimal control strategy. This robot is end-to-end trained, right? Which is a type of robotics that really only became available in like 2014, 2015, and I was working at a startup that was trying to do it. But it's a fundamentally different way of doing robotics where rather than pursuing some optimal control strategy with a bunch of physics equations and solving that and then having your motors try to get to specific joint positions, in this type of robotics, you're basically using a neural net to tell the motors what to do. So end-to-end, which basically means from one end of the system to the other. There's a neural net that takes in the input from the camera and maybe some joint positions, and then gives you the exact output that the commands should be. So everything is going through a neural net. And the way you can tell is just how irregular and instant, right? Like if you look at the footsteps, every single footstep is different, right? Let's put it a little more HD so you guys can see better. But every single one of the footsteps of this little robot looks different. Every single one of the arm movements, like none of them are the same. Versus if you look at the Boston Dynamics robot, they're all the same. There's a very specific foot like stride length, very specific knee positions, very specific ankle positions. And even though this type of optimal control is much more impressive and much more safe, if you want to say it, it actually works quite well, I think this is actually not the future, because this type of stuff is just too much planning. I think the reality is that the way robotics is going, it's going to be end-to-end. It's just going to be a neural net that outputs joint commands and joint velocities, and then you get kind of the more organic-looking movement of these little robots, right? But the problem with that is that kind of end-to-end neural network-based control is also a lot more sloppy. So there's no guarantees. These robots kind of fall down all the time. See, that one just like kind of fell down for no reason. But it also allows you to do all these kind of weird learned behaviors. Like they learn all these little micro behaviors that you would never get from an optimal control strategy, right? Like even just the way that they turn, right? They like kind of like move their arm like this, and then it kind of makes them fall down that way, and then they turn that way. So that's a little difference between kind of the optimal control of the Boston Dynamics, which is kind of like a fancy inverted pendulum, and then the reinforcement learning kind of end-to-end neural network-based control that you're seeing here in these little soccer robots. Cool. And obviously, if you're doing robotics kind of in the modern world, in the modern era, you're basically doing everything in simulation, right? So these robots are trained almost entirely in simulation, and then they apply it at the very last second. And this demo I thought was beautiful here, but they have the little robot, and then they have this lady here, like she tries to interrupt them. So this is like adorable video, but the little robot's trying to get to the ball. You see, and she knocks it down, and it just keeps going. Like, look at it. Look at this little robot. It wants to get to that ball, and it's like, oh no, and it misses it. All right, and it's trying. Ooh, boom! Look at that. You see that? See that how like it kicked with its right foot. So it obviously has a preference for the right foot, but then if the ball happens to be in the left foot, you see that left foot kick. So that's the kind of like micro, like almost like organic skills that you get when you use this kind of reinforcement learning based control or neural network based control. You get more kind of diversity. Cool. So let's actually dig into the details of this paper. This is a very long paper. This is almost like 30 pages long. Yeah, 34 pages long. So I don't know if we're going to get through all of this. So I think we're going to do kind of the fast strategy. So in order to read this paper a little faster, we're going to kind of skip through some of these things. We're going to read the abstract, probably the different figures. Usually the figures are the best in terms of bang for the buck. If you read all the figures in a paper, you probably have 80% of the paper. So we're probably going to do that. So let's scroll up. Let's read this abstract. We investigate whether deep reinforcement learning, deep RL, is able to synthesize sophisticated and safe movement skills at low-cost miniature humanoid robot that can be composed into complex behavioral strategies in dynamic environment. We use deep RL to train a humanoid robot with 20 actuated joints, so 20 degrees of freedom. And actually, we can compare this. So Boston Dynamics Atlas degrees of freedom. 28. So Atlas has 28 degrees of freedom. So this Boston Dynamics, which means 28 individual basically joints. So your elbow is 1 degree of freedom, right? But your wrist actually has multiple. Your wrist has this degree of freedom, it has this degree of freedom, and it has the rotation as well. So your wrist has 3 degrees of freedom. Go 20 degrees of freedom. We first train individual skills in isolation and then compose those skills in end-to-end in a self-play. So a couple different pieces here. Self-play, and this is DeepMind is famous for their self-play, right? Their Go and their Go robot, their Dota robot, a lot of that was done in a self-play kind of setting where the agent kind of plays itself in simulation, and then by doing that, it can get a lot of experience. So we see self-play. We see here individual skills, right? So some kind of curriculum-based strategy where you're learning first maybe mini games where they learn how to kick, they learn how to run, and then they maybe learn how to get up. And then each of those little mini games basically are their own little reinforcement learning problem. And then once you master all of those, right, the curriculum approach, then you get more advanced problems. Dynamic movement, such as here are all the different little skills. You got rapid fall recovery, walking, turning, kicking, and more. Transitions between them in a smooth and stable and efficient manner, well beyond what is intuitively expected from the robot. And this is key, right? So we were just talking about kind of the difference between optimal control and kind of neural network based end-to-end control. And those aren't like strict definitions. Those are more kind of strategies. At this point, there probably is a little bit of deep learning on the Boston Dynamics robot. But you're never going to see the Boston Dynamics robot do something unexpected. Every single one of these motions is expected and programmed by the people who wrote the software, right? There's literally nothing here that is unusual. But when you take one of these little robots and you're executing it live from a neural net, something that it's been trained in simulation for thousands of iterations in a self-play thing, there's going to be a huge amount of emergent behaviors, right? All these little tiny little tricks that the robot has learned that, like here, for example, the way that it decides to move the ball when it's up against the slope, right? Like it's almost impossible to predict what it's going to do what it's going to do because the entire control loop is running on a neural net. The agents developed a basic strategic understanding of the game and learned to anticipate ball movements and to block opponent shots. The full range of behaviors emerged from a small set of simple rewards. Our agents were trained in a simulation and transferred to real robots 0 shot. So what do they mean by this? They mean that one of the hardest problems in robotics is you train all of it in simulation, and then when you try to execute it in the real world, it doesn't quite work, right? The weight distribution of the joints isn't quite the same. The friction between the feet and the ground isn't quite the same, right? So like the simulation doesn't perfectly capture reality, and this problem is called sim-to-real transfer. But here, they're literally telling you transfer to real robots 0 shot, which means they didn't even do any sim-to-real transfer. They just straight up took the simulated little brain that they trained in simulation, that little neural net, they put it directly on the real robot, and it works. So that is very impressive, right? We found that a combination of sufficiently high frequency control, targeted dynamics randomization, this is interesting. This is where inside the simulation, they change the friction, they change the weight of different joints, they change the power of different joints. And by doing that, the robot gets pretty good at working under a wide variety of conditions. Perturbations during training and simulation enabled good quality transfer despite significant unmodeled effects and variations across robot instances. Although the robots are inherently fragile, minor hardware modifications together with basic regularization of behavior during training led the robots to learn safe and effective movements while still performing in a dynamic and agile way. Indeed, even though the agents were optimized for scoring, in experiments they walked 156% faster, took 63% less time, and kicked 24% faster than a scripted baseline. So scripted baseline means there's probably some strategy that something like a animator, very similar to an animator, someone sat there and like individually moved the joints and created a scripted behavior. And the behaviors that these robots learned in simulation using reinforcement learning are significantly better, right? So you see here, these numbers here, no joke. right? Hard evidence that the learned behaviors are more efficient and faster and better than the hard-coded behaviors, right? So to me, the fact that you get this improvement over the scripted baseline, right, it makes this entire thing is a scripted baseline, right? All of these behaviors that the Atlas robot does are scripted. So that's a big improvement. Introduction, creating a general embodied intelligence. So embodied just basically means it has a body, right? That's kind of something that robotics people talk about a lot, is the idea of embodied intelligence. Blah, blah, blah. Little 1994 paper. Deep reinforcement learning. Perception driven. RL yields generality and scalability. Yeah, the ability to train in simulation and then deploy in the real world is huge and very important for reinforcement learning. High quality quadruped-legged robots. Yeah, everybody loves the quadrupeds, but you know, I really think there's something to the humanoids, because humanoids, there's just like an inherent anthropomorphization that occurs, and like they're just so much more like appealing. Like for some reason I just care so much more about these little humanoids than I do about the Spot robot, right? It's a little human bias. Okay, you got more works here. You got climbing, soccer skills, blah, 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 creating sophisticated long horizon multi-skill behaviors. Sports like soccer showcase many of the hallmarks of human sensory motor intelligence. Players also need to coordinate movements over long time scales to achieve tactical coordinated play. Yeah, so as soon as you get into the real world and you're dealing with this problem of embodied intelligence, one of the more difficult things is that you have now this time dimension, and the behaviors are not just within like a 2-second window. It's not just, okay, I need to move my leg here, but then you have the, okay, well, there's a long-term strategy, right? So like, where are you leaving with the ball? What's going on? Like, what's your opponent doing? There's layers and layers of complexity as you continue to expand the time window that you consider, right? So it's not just about getting these little micro behaviors. It's about getting the like longer strategic behaviors as well, of like, hey, I'm moving my leg, but the reason I'm moving my leg in this second is so I can get over to that part of the field, because that's where I want to be. In this work, we studied the whole body control and object interaction of small humanoids in dynamic multi-agent environments. Low cost, 20 controllable joints, simplified 1v1 game. Yeah, so I mean, there's nothing that really prevents you from doing, I think the reason they did 1v1 is just because it's easier to do. But I've seen plenty of reinforcement learning papers in simulation where you have multiple robots and they play together and they figure out strategies to actually work in a team-like manner. Deep RL to synthesize dynamic and agile movement skills. We trained the agents in simulation and transferred them into the real robot, right? Sim to real transfer. Sim to real transfer is possible even for low-cost robots. We introduced both the simulated and the real soccer environments that we use to train the agent, as well as the robot hardware. All right, here we go. First figure, we got the simulated environment here on the left, which is where the overwhelming majority of the training, I think literally all the training, occurs in simulation. And then the real environment here, which is basically just these little rubber bricks. I don't know what this is, little rubber tiles and then little foam ramps. And here you go. The physical robot is a Robotis OP3. So let's see. Robotis OP3. Here we go. What is it? A Robotis OP3 has, let's see, here we go. Here are the specs of this little buddy. We have an Intel Core i3 processor. We have 8 gigabytes of RAM at a 2 megahertz clock speed. We have 128 gigabytes of solid state disk storage. This is basically running a Linux, or I guess Windows. I don't know why you would run Windows on a robot. That seems really weird. You got 5G internet connection if you want it, or Bluetooth. You got a Logitech camera, so 1920 by 1080. That is probably not the resolution at which they're running these things. They probably downsample that to something like 512 by 512 or even 128 by 128. These are the actual actuators. I have actually some MX28s somewhere in this house, but this is the newer version, XM430s. These are the little servos in there. So for example, reduce size and torque, probably more smooth motion control, and etc. See, 20 degrees of freedom. Where's the... It doesn't actually sound like they have a accelerator or like a neural network hardware, right? It sounds like they literally just have, they're just running inference on a GPU or on the local CPU. Here's all the instructions for charging the little robot and so on. So these aren't actually its eyes, right? It actually has one central eye, but they put these little two nubs to make it look like it has eyes. Well, these are cute. I like these little robots. They look very cute. Okay. So they have their simulated environment. They have their real environment. They train everything in the simulation, and then they transfer it to the real world, which basically just means they take that brain that they trained in the simulation and they put it on the real robot, and then the real robot just works. And the reason it just works is because in simulation, they're constantly changing the weight and even the length, right? So like in simulation, the robot might suddenly have its left leg a little bit longer than the right leg. The right foot might be a little bit heavier than the left foot. The arm might be a little bit longer. The motor that drives the knee might be a little bit weaker than the motor that drives the elbow or something like that. And by constantly changing those parameters in simulation, the brain that learns to control these simulated robots actually gets very good at controlling a robot that has weirdness to it. Because in the real world, the real robots are going to be a little bit weird, right? Like some of them are going to have slightly worse servos. They're going to have like maybe a loose elbow or something like that. So they need to basically make the robots in simulation not perfect, but the opposite of that, very unperfect, in order for the brain to get good at them. Okay, so it seems like they're playing this 1v1 game where basically you need to get the ball in the net. And you see how they say mocap marker. So this is, mocap stands for motion capture. And you see these little mocap on the robot here. You see how this got like these little balls? Those balls are very reflective when it comes to infrared cameras. So basically you can track exactly where the robot is. So they know exactly where the robots are in real world. We trained agents in simulation in a custom soccer environment and then transferred these policies to a corresponding real environment. The simulated environment uses Mujoko. So Mujoko is very popular in the robotics world. It actually recently got open sourced. DeepMind Control Suite. This is DeepMind's own little stack that's based on top of Mujoko. The environment consists of a soccer pitch that is 5 meters by 4 meters, blah, blah, blah. The real pitch is covered with rubber floor tiles. Score a goal while preventing the opponent from scoring. In the simulation, the agent is rewarded for scoring a goal. Okay, the agent acts at 40 hertz, so 40 times per second. That's how fast the control loop is running on this robot, which is actually quite small, or not quite small, quite fast. 40 hertz, like to me, that's telling me that the neural net is actually very small. The neural net that actually executes. But maybe, wait a second. Let's keep reading here. Maybe UT is the filtered control applied to the robot, and AT is the action output by the policy. Okay. So it's actually a little bit more complicated. So the actual control signal that comes to the robot is actually a weighted combination of the policy output. So the policy is the actual neural net. So the neural net is outputting AT, and then the control policy applied to the robot, which is basically just trying to keep the joints in a specific position, is UT. And you see here how it's a weighted combination of those two. It's the action at time t is the 0.8 times the action at the previous, or the position at the previous step, and then AT, which is the action of the policy. The filtered actions are fed to PID controllers. This is very classic type of control system where you have proportional, integral, and derivative. I think basically it's just first order, second order, and third order, where basically you try to control the difference in position, then the difference in velocity, and then finally the difference in acceleration or something like that. It's like everybody has seen this PID control. Yep, here you go. PID controller. So PID, you have KI, which is basically just trying to make sure that the positions match. That's this red line. That's the P, right? Or no, the P is this green line here, right? The I is this red line. And then the D is this black line. And here, this blue line is what you're trying to match. So in a robot, it might be like, okay, I want my knee to be at position 0, and now I want my knee to be at position 1, right? And it's like, okay, well, how do you move the joint of that robot such that it goes from position 0 to position 1, and this is the actual curve, right? So the controller is actually saying, okay, move here, move here, move here, based on the velocity and the current position. Right, so this is the actual math for a PID controller. And PID controllers are everywhere. There's a PID controller that controls the temperature in your house, probably, in your thermostat. The agent's observation consists of proprioception and game state information. So proprioception consists of joint positions, IMU readings, and the state of the exponential action filter. So it knows the position of its joints. The IMU is an inertial measurement unit. It's basically what you have in a phone, right? It's like an accelerometer. It tells you the orientation of your phone, and kind of estimates the angular velocity and things like that. So they have one of those on the actual robot too. So the robot has basically the equivalent of a human inner ear. It can kind of know if it's like this tilted, or if it's like this tilted, or if it's like getting thrown forward, and so on. The game state information obtained via motion capture. So this is a little bit of cheating. To me, I never liked this. I never liked that these robots, they use mocap systems. So the robot knows exactly where it is in the field, right? When you're training in simulation, it's very easy to say, okay, well, I'm just going to tell the robot exactly where it is, and exactly where all the joints are, and exactly where its opponent is, and exactly where the ball is, right? So it has this kind of omniscient sense of everything in the environment. And when they transfer it to the real world, they still do that, right? They still put these little mocap markers on the robot so that the robot knows exactly where it is at all times in this field, and it knows where the opponent is, and it knows where the ball is, and it knows where the net is. So obviously that's going to lead to more impressive results because you're giving the agent more signal from which it can execute a better policy. But the problem is that, to me, that's not realistic, right? I would much prefer if the robot had to basically learn to execute all these actions entirely from the vision, right? Entirely from its camera, right? Because then you would see completely different behaviors. Then you would see kind of looking behaviors where it would actually spend a lot of effort trying to figure out, where do I need to look? I need to find the ball, and it would try to find the ball, right? Rather than the behaviors you see now where it knows where the ball is, right? It's getting the exact position of the ball in 3D space from the mocap system. So you can actually tell, right? Like here, you see how it kicks the ball, for example, right here. Let's slow it down, but it kicks the ball, and the other robot, you see right here, the other robot only sees this corner. So as far as the other robot understands, it doesn't know where the ball is. But then as soon as it kicks the ball, you see how this robot, it knows to turn to the left because it knows that the ball is there, right? Versus I feel like if it was forced to do everything from its vision system, it wouldn't have that kind of like omniscient knowledge of where the ball is and where the opponent is, and thus have different behaviors. Yeah, so it knows the agent velocity, the ball location, opponent location, location of the two goals, and so on. Yeah. Locations are given as two-dimensional vectors corresponding to horizontal coordinates in the egocentric frame. So egocentric frame means that everything is relative to the robot's center of mass. Basically, it's egocentric as in the center of me, of myself. All proprioceptive observations, as well as the observations agent's velocity, are stacked at the 5 most recent time steps. So rather than just telling the robot, hey, this is the position of your elbow, it also says here are the 4 previous positions of your elbow, and that allows you to basically have a little bit of a notion of time and velocity. So for example here, for each of the joint positions, there's 20 degrees of freedom, so 20 joints in the robot. But then also it's 5 times that, which means there's 100 numbers there because it's the last 5 positions of all 20 joints. So you have the linear acceleration, angular velocity, you have the gravity direction, you have the previous action. So not only do you have the position of the joints, but you have the action. And the reason those are different is because you have a control loop that's trying to match the specific action or the position of the joint to the action, but the control loop is separate from the neural net. You got ball position. This is just a 2D point because it's kind of from a top down. You have opponent position, goal position, opponent goal position, agent velocity, ball velocity, and opponent velocity. Yeah, and these are the things that I wish they didn't give it explicitly. I really wish they just let the robot figure all this part out, right? The reason they include these is because it works way faster, it learns way faster, and it works way better. But I feel like we want to get to a state of deep reinforcement learning in robotics that you don't have to give the robot all this extra game state. It just figures it out from vision. So here's our little buddy, our little robotus. You see how it's got these little bumpers in the front and the back. So these little bumpers here means that whenever it falls, it can catch it doesn't break the robot. And you actually see a similar kind of design in the Atlas robot. So you see how all along the outside of this Atlas robot, there's this almost kind of like a cage, right? You see how everything is protected in this cage so that if the robot were to ever fall, it's not going to break the robot. And you see kind of a similar design here where it has these little blue kind of bumpers in the front and the back so that if it falls forward, falls backwards, it doesn't hurt itself. 51 centimeters tall and weighs 3.5 kilograms, so kind of little toddler-sized robot. Controlled by the servos, it sends target angles and then uses position control mode. So position control mode means that it's trying to match a position. The controller on the robot is trying to match a position. And there's different control strategies. There's position control, but then there's also velocity control. Right? Velocity control is a different type of control strategy. Position control is actually the easiest one. And actually, in terms of, you know how we were showing the PID controller, right? So PID controller has the 3 parts. They're only using the P. So this is only a P controller. It doesn't have the integral or the derivative terms, right? So no I and D, just P. Each actuator has a magnetic rotary encoder. So this is the sensor on each servo that tells that is how you know the exact position of that joint. Has an IMU. It's running Nuke, Dynamixel SDK, Python API. Dynamixel is the company that makes these servos. The camera is operating at 30 frames per second, which is weird, right? The camera is operating at 30 frames per second, but the control loop is running at 40 hertz, which is weird. Like, why is there a mismatch there, right? Why is there a 10 hertz difference? The robot ball positions and orientations are provided by a motion capture system. So they're using ROS. ROS is the robotic operating system. It's kind of a toolkit, a set of software, right? Different software modules that people have written over time, and it basically has a bunch of stuff already built. So if you're trying to do robotics from scratch, using ROS is a great way to save yourself a bunch of work. But I also feel like ROS is kind of unpopular in other ways because it's also very heavy, right? So even though you save yourself a bunch of work by not having to implement a bunch of things that people have already implemented, you kind of have to do all this extra stuff. You have to learn about ROS. You have to learn how to use ROS, all these ROS abstractions. So it has kind of the general problem of too many abstractions. Method. All right, our aim is to train an agent, including walking, kicking. Behaviors do not emerge. Splitting training into 2 stages. In the first stage, we train teacher policies, okay, for 2 specific skills, getting up from the ground and scoring against an untrained opponent. When training on the latter skill, the episode terminates. So episode is an individual unit of simulation, right? You can think of it like one game, except it doesn't need to be like a full game. It can just be like a spawn the robot kicks the ball, and then it ends the episode. Without this termination, the agent finds the local minima and learns to roll the ground towards the ball and knock it to the goal. In the second stage, the teacher policies are used to regularize the agent. So you have this kind of teacher-student paradigm, right? Like you see that in distillation. And here in robotics, they have teacher networks, and then they have... It's kind of an interesting way to do kind of curriculum learning, right? Where rather than training a network to solve one easy problem and then taking that same network and trying to basically learn a new task that is more complicated, they basically have a network that learns the simple problem, and then that network acts as a teacher policy for a network on a new task, which is kind of interesting. We use a form of self-play where the opponents are sampled from previous versions of the trained agent. This is a form of automatic curriculum learning. Yeah, and this is something that DeepMind is very well known for, right? DeepMind is very famous for their work on Go and chess and things like that. And the way that you train those is you basically, in any kind of self-play scenario, you need your opponent to be roughly at your skill level. If you're playing against people that are way better than you all the time, you're never going to get better. If you're playing against people that are way worse than you, you're never going to get better. So you need to be playing against people that are kind of at your skill level. So DeepMind has kind of perfected this automated curriculum learning self-play approach where you can basically play. They get the agents to play against slightly older or slightly different versions of themselves that are roughly about the same strength. To facilitate transfer, they do domain randomization. So this is changing the weights of the different links and so on. Random perturbations, sensor noise, and delays. So here are other things that they can add. Sensor noise, where in simulation, you know the exact position of all these joints, but rather than giving the robot the exact position of all the joints, mess with the joint positions, right? Sometimes tell it that its knee is in a different position than it actually is. And delays, so simulating all the different things that could go wrong in a robot, right? In terms of sensor noise, the laggy feedback, and so on. We modeled the soccer environment as a gamma discounted, partially observable Markov decision process. So this is, now they're going to give you the classic definition of reinforcement learning. So this is reinforcement learning without the deep, right? So deep reinforcement learning is merely reinforcement learning where you're using a deep neural network as one of the function approximators. But reinforcement learning is much older than that, and it's also much more kind of rigorously defined. So there's all these different parts, and here you have the different parts. You have the state space, S, right? You have the action A, right? So in this robot, there's 20 joints, so it's a 20-dimensional action vector, right? So that's your S and your A. Your P, let's see, where's the P? Where's the P? Where's the P? Can't see it. Your R is going to be your reward. Where's the reward? Here we go. A reward as a function of the new state. There's your reward. You have your P0, which is probably your initial state. Where's the definition? System dynamics. Okay, so actually we learned what the system dynamics are. It's P, right? So that's how the system behaves. Given a certain action, how is it going to behave? And then your gamma. Gamma is a discount factor. So when you're training reinforcement learning agents, they're fundamentally whenever you're training a deep neural network, you have a loss, right? And your back propagation is trying to reduce the loss, is trying to bring the loss down. In a reinforcement learning, your back propagation is trying to increase the reward, right? So how much reward do you get per step? And the gamma discount, what it does is it says the reward that I receive now is more important than the reward that I receive later, right? The reward that I receive 100 steps from now isn't as important as the reward that I receive now. And how much more important is determined by this gamma. And usually gamma is something like 0.99, right? Or something like that, where it's basically, it just means that as you go forward in time, the reward decreases. Players' stochastic policy. So stochastic here just refers to the fact that there's a little bit of randomness in there. You have observation action history, right? So observation is key here, right? Because they call it partially observable. And the word there, partially observable, refers to the fact that the robot does not know exactly what its joint positions are or what its positions in the environment or anything, right? The state space, this stuff up here that they were describing, the robot doesn't have perfect access to that. It has partial access to it. Because, of course, they're going to be changing it, right? They're going to be messing with it, jittering it. You see here all the sensor noise, delays, perturbations, stuff like that. So in a Markov decision process is perfect. You know exactly where you are. An example of that would be like chess or Go, right? In chess and Go, it's a perfect Markov decision process in that you know exactly the state of the chessboard, right? But any kind of real-world robotics use case, you don't know the exact position of all the joints because there's going to be sensor noise and you might not know exactly what's going on. So it's a partially observable Markov decision process. So a much more difficult problem. The observation history is needed to compensate for the partial observability of the environment, such as the feedback latency and the model variations used for domain randomization. Okay, so here's your reward. So your reward is you're going to have case steps in an episode, right? Case steps in a certain, you could think of it like if you have one game of chess, maybe the game of chess is 100 moves. I don't know how many moves a normal game of chess is, but you have 100 moves. For each move, you're going to have some reward. Each step within the episode is going to have some reward. And here you see the total reward is the sum of all rewards up until that point, right? From k equals 1 to k of this reward here, which is a function of the state, and then this alpha, which I think is basically just a discount. And you finally get a policy. Oh, let's make that green. And then a trajectory. Trajectory is the actual set, or the state, the trajectory in state space, but it's also here in action space. So it's like the specific actions that I took and the states that I ended up at and all the rewards that I received. Over horizon length t, this is just how long the episode is. Okay, here we go. We trained soccer agents in 2 stages. In the first stage, we train a separate soccer teacher and a get-up teacher. So they have 2 different teachers here. In the second stage, we distill these 2 teachers. into a single agent that can get up from the ground and play soccer. So you have teacher networks for specific policies or specific tasks, and then you distill a new network that plays or that does both of those tasks. The second stage also incorporates self-play. The opponent is uniformly randomly sampled from a pool that consists of policy snapshots from earlier in training. This is just a fancier way of saying model checkpoints. We found that this two-stage approach leads to qualitatively better behavior and improved sim-to-real transfer compared to training an agent from scratch for the 1v1 soccer task. Yeah, so these kind of like curriculum learning approaches, right, where you train simpler tasks and then use that to train harder tasks. I think that's very important. And I think as we move more and more into the future, that's going to be kind of the same way that human education is like a very complicated task where you basically have this like 20-year system and process of like iteratively incrementing the difficulty of the task that humans. Hello, Mahesh. Your explanation is very good. Surprised that I am understanding all these EC and mechanical topics so easily. You're talking about kind of the robot stuff here. Look at this. Dynamixel SDK, which is the company that makes the servos, Robotic operating system, and then C++. So the overwhelming majority of robots are programmed in C++. You can program robots in Python, and I've done that, but it's really slow. So usually what people do is the robot control loop is implemented in C++, and then the neural network is trained in Python in simulation, but then you take that neural network, which was basically designed and built in Python and trained in Python, and you compile it into an actual like compiled model file, and then you run that model inference in C++ code. That's generally how people do robotics, is they do everything in Python, and then once you actually put it on the real robot, you do everything in C++. Okay, we were looking at this kind of two-stage strategy here. So the first stage, you have DMPO. This is the actual. So replay, this is the experience. So this is all the times in simulation. This is hundreds of episodes in simulation, right? Usually this kind of cylindrical structure in these kind of diagrams represents a database, and a replay is basically like a big giant database of all the experience that the robot's collected, right? The teacher policy takes actions, and then it gets the rewards, right? And then you basically do back propagation on the teacher policy, say, okay, for this state, I took this action, and I got this reward. And you do that with the get up task, you do that with the soccer task. These teachers get very good at that specific task. And then you're going to take those teachers here. Here they have a KL, which stands for the KL divergence. And then you have a replay here for the full soccer game, or the full soccer task, right? And that gets used to train the 1v1 policy. And the 1v1 policy actually plays itself as well. So this is like kind of simplified here, this block diagram, right? That's not necessarily showing you everything, but you have the basic components here, right? You have your databases of experience, right? Sometimes called the replay. You got the actual environment, which is either going to be the simulation. So this is either the simulation or the real environment. So the actual real physical, like this, even though I don't think that they did any learning in the real environment. All the learning was done in simulation. So both of the environment blocks here are simulation. And then you have your policies from your teacher policies, which are basically the early versions, which are used to distill the final policy, which is the one that you see in these videos. The final policy is this one here, the 1v1 policy. System dynamics, initial state distribution, give rise to a distribution over trajectories. So here you have the policy. So the policy takes an action A of t given the state S of t. Here you have the system dynamics, which is basically physics. and it says given the state and the action, this is the new state. So given my current robot position and the action that I want to take, what is going to be my new state? And that's going to give you, that's given by the system dynamics function here. You have the policy, which is the neural net. Here you have this capital letter pi here. This means multiplication, so you're multiplying all of these together from time step 0 to capital T, which is the horizon. And this is one of the things that I don't like about reinforcement learning, is that it's actually conceptually quite simple, and most people understand all these different conceptual parts. It's just that because it has this kind of historical legacy, right, and it has all these extra terminology, right? It's like, rather than calling it, I don't know, like data, they call it an episode, right? Rather than saying a neural net, they call it the policy. Rather than saying the number of steps or the number of samples of data that you have, they call it the horizon length, right? So like there's all these like observation action history. Like these are actually quite simple to understand conceptually, right? It's a very simple kind of system of like, okay, I take a state, I have a state, I take an action, I get in a new state, I have a policy which gives me my action given a state, I have some rewards, but they have all this extra terminology which actually makes it sound like it's much more complicated than it really is. And that happens in almost all kinds of math and all kinds of things in general, right? Where it's like over time you accumulate this jargon and this kind of terminology that actually serves to make things more complicated when they shouldn't be more complicated, right? You should try to make things easier over time so that new people can understand it better, but instead you end up getting this problem of like kind of over-jargonization of a field. So maximum a posteriori policy optimization. So if you guys have heard of PPO, right, that's a very common reinforcement learning algorithm. This is a variant of that. And then here they call distributional critics. So there's a family of reinforcement learning approaches called actor critics, where the actor is the policy that determines the action, which is obviously a neural net, right? Because a neural net is the best function approximator that we know of, and it's a function approximator that gets better over time. It learns. And then a critic. A critic is kind of a type of almost like a value function, which is like, hey, given this state, given this action, given some combination of those types of information, what is the reward, right? So the critic criticizes the policy. So almost, if you want to think of it, it's conceptually similar to the idea of a GAN, right? In a GAN, you have a generator and a discriminator. And in reinforcement learning, that same kind of idea, you have an actor and then you have a critic. And let's see, TF agents. So let's see, here are a bunch of different, let me see if they have a list of them. Yeah. So these are different reinforcement learning algorithms. So PPO, right? That's kind of the simple version of this. And then DMPO is an even more complicated version of that. But then SAC is also another very popular one. And this is the soft actor critic. It's kind of, I think, the first actor critic. Maybe not. There's probably definitely way better or way earlier versions of the soft actor critic. Okay. We parameterize the policy as a deep feed-forward neural network with parameters theta. And in order to better handle partial observability, we provide a history length of H5. So it not only does it know its joint positions, but it knows its joint positions and the previous 5 joint positions. The DMPO agent outputs the mean and diagonal covariance of a multivariate Gaussian. That's the distribution here. So a lot of times in these reinforcement learning systems, rather than actually outputting the exact action to take, it outputs the distribution of the action to take, and then you just simply sample from that distribution, right? So rather than saying, hey, given this current state, I should move my leg to this position, it says, given this current state, I should move my leg to a position that is parameterized by a Gaussian, or that is defined by a Gaussian, which with this mean and this diagonal or this covariance, which is just a fancy way of saying standard deviation. Details in the agent are given in Appendix A2. Okay. Training. Let's see. What are we at? 55 minutes? Okay, we still got plenty of time. I just want to make sure that we get to all the parts of this paper because it's very long. So, soccer teacher is trained to score as many goals as possible. Episodes terminate when the agent falls over, goes out of bounds, and enters the goal penalty area. Okay, so episodes, again, are one individual kind of atomic unit of experience. Right, so in simulation, you can run a lot of episodes very quickly because as soon as the robot falls over in simulation, you end it and you restart a new game, right? And that's like almost instant. Versus in the real world, if the robot fell over, you would have to basically stop everything. The human's going to have to go in there, take the robot, put it back up. Then we're going to have to walk all the way out of the thing and then restart everything. So collecting episodes in the real world is significantly more time intensive and human intensive than it is in simulation. In simulation, you can collect a lot of them a lot faster, and you can do it in parallel. Both players are initialized at a default standing pose. I think that's this little pose here. So you see this, it's called a T pose, right? You see it's like standing like this. It's a little T pose. The agent could immediately learn to avoid the opponent, but no further complex interaction. The total reward is a weighted sum over reward components. Okay, so here are all the different rewards. And sometimes in reinforcement learning, there's people that kind of in tongue-in-cheek, they say reward shaping, I don't know, reward optimization, kind of like a loss function engineer, reward function engineer, where like in these complicated reinforcement learning systems, knowing exactly what reward to pick and how to choose all these magic numbers here. So all these numbers here are chosen by a human, right? So you get a +1 when the agent scores a goal, right? You get a -1 when the opponent scores a goal. You get a reward based on the magnitude of the agent's velocity towards the ball, right? And that's only worth 0.05. The magnitude of the player's forward velocity is worth 0.1. So why is this worth 0.1 and this worth 0.05? And there is no good answer to that. The answer to that is that some human who was sitting here just sat there and played with enough with the system that they decided that a goal is worth 1,000 more points than a penalty or whatever. Or no, this is not different use of the word penalty, but this is a regularization where you want the cosine of the angle between the player's velocity and the heading of the opponent if the player is within 1 meter of the opponent. This discourages the agents from interfering and fouling with the opponent. So this one doesn't seem that bad. This is only, what is this? 1, 2, 3, 4, 5. This is like maybe 10 different reward terms. But if you guys remember the Dota 2 paper from OpenAI, that paper was ridiculous. They had like almost like 50 different reward terms, each with different weights. And that was kind of definitely reward engineering. But ideally, we'd like to get to a point kind of in the reinforcement learning world that we don't have to be doing this reward shaping, right? You don't have to be sitting there and coming up with all these different magic numbers and like massaging all the different terms in this reward such that you get the best possible policy, right? So here's another regularization that penalizes the torque. And this is something you see a lot in robotics with reinforcement learning, is that you usually have these regularization terms that penalize really fast motion. So total amount of torque, joint speed, and things like that. And that prevents the robot from kind of jerking really quickly, because when you're training in simulation, usually the robot learns pretty quickly that it needs to move as fast as possible, right? So in order to move as fast as possible in simulation, it just literally maxes out the joint torques every single time. But if you max out the joint torques every single time on a real robot, you're going to burn the robot out like pretty quickly. It's, you know what I'm saying? You don't want to be running these servos at max speed, max joint torque constantly. So in almost every single deep reinforcement learning with real world robots, especially where they do this real sim to real transfer, they have these penalties, right? These regularization terms in the reward and in the loss for reducing the torque and the speed of the robots, or the robots, yeah. The joint key poses used to train the GetUp teacher, extracted from a scripted GetUp controller. Okay, so these little humanoid robots, right? They've been around for a while. So we can actually Robotis OP1, right? Robotis OP. So they're using the OP3, but the OP1 is like quite ancient at this point. Like we're talking like years and years, and people do all kinds of crazy stuff with these, right? Like people have done, like I've seen like a dancing miniature humanoid robot, like yeah, people have these like shows where like they basically have them sit around and they dance and stuff like that. So people have been playing with these little humanoid robots long enough that they have like these very good scripted actions, right? So someone sat here and they made this scripted getup, right? And what is a getup? A getup is basically, hey, if you fall on your back, here is a set of actions that pretty much guarantee that you'll end up back on your feet, right? And there's like this thing with the arms where they like lean forward and then they kind of do this little push up, right? You see it right here. The robot does this little push up and then it gets on its knees and then it stands up. So rather than trying to train a get-up behavior from scratch, they start it from this scripted behavior. So sometimes you call this bootstrapping. So in reinforcement learning, rather than learning from scratch, you can bootstrap it from a already existing policy. And in this case, the policy is a hand-designed human policy, right? So that's what they're doing here. Training a separate teacher resulted in qualitatively better final agent behavior. Okay, extracted 3 key poses, interpolating between the key poses. We instead use the key poses to guide learning but do not constrain the final behavior. The GetUp teacher is trained to reach any target pose. Target torso orientation. Okay, so this is where it wants to end up. Condition both the actor and the critic. So the actor and the critic, right, are 2 different neural networks. You have a neural network that represents the actor and a neural network that represents the critic. And what they mean by condition here, that basically just means they're giving the actor these joint positions, or these joint positions and orientations, and they're giving the critic the joint positions and orientations. So anytime you see an equation where you have this little parallel bar, like this bar here, so AT bar ST, that means conditioned on. So this is the policy given the action state conditioned on the state here, S of T. So that's what they mean here, conditioned on. So the actor is conditioned on these P and G, and the critic is also conditioned on P and G. The agent is trained to maximize. So trained to maximize, right? This is a reinforcement learning system, which means that you're not reducing a loss, you're maximizing a reward. Or you could think of it like minimizing the negative reward. Same thing. Maximizing a thing is the same as minimizing that negative of that thing. So the reward that they're using here is negative P tilde T, G tilde T. So these are the P target and G target, where P tilde is the scaled error. So you see here they have the target position, they have, I guess, the current position. You have the L2 difference between them, right? So the two parallel bars there with the 2, that means the L2 loss. You have pi minus, I don't know what the pi is. I guess it's because it's a joint position, and joint positions are usually encoded in radians. And scaled angle and actual gravity direction. Okay. Conditioning the converged policy on the last key pose makes the agent stand up, and we reuse this as the get up teacher. Okay, so now they've trained this neural network that knows how to get up from the ground. And that neural network only knows how to do that, right? It doesn't know how to play soccer, doesn't know how to do anything. It's just a reinforcement learning trained neural network that can get up from the ground. It can give you the set of joint angles to get up from the ground. But now they want to distill it, right? They don't want to just use that neural network. They want to use that neural network to train the neural network that's actually going to learn to play soccer. So in the second stage, the agent competes against increasingly stronger opponents while regularizing its behavior to the teacher policies. That's quite interesting, right? So I wonder how they alternate it, right? That would be pretty cool, right? Do they do 10 episodes of self-play and then 1 episode of get up and then 1 episode of kicking? Like, do they kind of do like a weird fancy schedule like that? Or is it like a weighted sum? Here you have a little bit more reward shaping here. If the agent is on the ground when goal is scored, and it receives a 0 for the scoring reward. Given both the soccer and the get-up teachers, the agent must learn to transition smoothly between these two skills. Since the teacher policies are trained in the same environment for the same embodiment, we can use policy distillation, which is just a fancy way of saying distillation, right? And it's like, this is kind of what I'm talking about with the terminology. Policy distillation is just distillation. The policy is a neural network. So why call it a policy? Just, very annoying. By adding a regularization term to encourage the output of the agent's policy to be similar to that of the teacher's. Unlike most prior work, in our setting, the teacher policies are useful in a mutually exclusive sets of states. Yeah, the get-up teacher is only useful in states where the agent is on the ground, and the soccer teacher is only useful in states where the agent is upright. Thus, the agent should only be regularized to one teacher at a time, right? So this is a good point. It means that you wouldn't want just a weighted sum, right? You don't want, when the robot is just running towards the ball, you don't want to basically penalize it because the policy of running towards the ball is significantly different from the policy of getting up, right? You only want the policy of the robot to be penalized for not looking like the policy of getting up whenever it's actually trying to get up, right? So it has this like property that the teacher policies are only applicable as regularization terms whenever you have a very specific condition, right? Depending on which state it is in. So they split the training objective into 2 components, one that combines the soccer training objective with KL regularization. So I guess this is the objective. Here you have, is this a J or is that a T? I don't know. But it's a function of pi's theta, which is pi is the policy, theta is the parameters that parameterize that policy. And then you have KL regularization. So KL regularization is a type of, basically a way to measure how similar two probability distributions are, right? And why are they using this? So the reason that you use KL regularization is because the policy here, right, this is a neural network. It doesn't output an action directly. What it outputs is a probability distribution, right? Scroll up here. What it's outputting is this. It's outputting the mean and diagonal covariance of a multivariate Gaussian. So it's giving you a Gaussian. So you're saying, hey, this Gaussian here and this Gaussian here. And I want to know how similar those two Gaussians are, right? And this KL divergence term is basically, you can think of it like an L1 or an L2 loss, but rather than an L1 or an L2 loss, which is between two like hard numbers, the KL gives you kind of basically the difference between two probability distributions in a way that kind of works pretty well, and kind of everyone uses it, to be honest. I feel like I haven't really seen like, this is kind of almost one of those things where it's like kind of like the ReLU versus GeLU kind of debate, where I feel like maybe if someone found something that was kind of like the KL divergence but different in some way, it might actually even work better, right? So there's still like fundamental research to be done to me, in my mind, about like why are we even using this KL divergence? Because one thing that's weird about the KL divergence is that it's not symmetric. So if you put this pi theta on this side and you put the pi f on this side, you would get a different KL term or KL number. So, right? Isn't that weird? You have a metric that is not symmetric, right? A minus B is different than B minus A. That's a weird way of saying it, but the distance from A to B is different from the distance from B to A. Okay, we're getting distracted though. So this is the expected value of this KL divergence, right? You have two policies here. You have the soccer teacher, and then you have the get up teacher. So these are the two teacher policies, right? The neural networks that learned how to do this get up task, and then the neural network that learned how to do this soccer task, which is just the kicking. Do they define what this lambda is here? I think this lambda is basically just some weighted term. Here you go. Weights lambda f and lambda g are adaptively adjusted such that there is no regularization once the agent's performance is above chosen thresholds. Okay, so this is the lambdas are the numbers that they change depending on the mutually exclusive conditions. So if you're getting up, the lambda f is going to be probably 1, and if you're getting up, the lambda g here, because it's what modulates the get up teacher, is going to be 1, and then the lambda f is probably going to be 0. But whenever you're playing soccer and you're standing up and you're trying to kick the ball, the lambda f is probably going to be 1, and then the lambda g, which is for the get up, is probably going to be 0. So those are the two things that they basically modulate. Okay. We are adaptively adjusted such that there is no regularization. Blah, blah, blah. Okay. Using a soft plus transform and clipping such to enforce. Yeah, so these lambda terms are basically between 0 and 1. Okay, when the agent's predicted return is less than QF, and once you have lambda f increased to 1, the agent effectively performs behavior cloning to the soccer teacher. So behavior cloning is whenever you're doing reinforcement learning, but rather than saying, hey, I'm trying to maximize reward, you're saying, hey, I want my policy that I'm executing to be exactly the same as this policy, which I'm considering to be like an oracle, right? Like the master policy. And behavior cloning is usually used whenever you're trying to match a human policy. So maybe you have a human that's controlling a robot, and then you say, okay, well, I'm going to train a reinforcement learning system to clone that human policy, right? So that's generally what behavior cloning is used for. Here, they're using it to try to get the 1v1 agent, 1v1 policy to basically match the get-up teacher or the soccer teacher, depending on which of those two is the more relevant one. This enabled the agent to improve beyond any simple scheduling of the teacher policies. Yeah, so actually this is the more interesting one, right? Is that whenever they introduce this, okay, we're going to be using these kind of curriculum approach where you have the get-up, you have the soccer, and then you have the 1v1 task. A naive and simple way of doing it would have been, hey, let's train only on the get up, then we'll train only on the soccer, and then we'll train only on the 1v1, right? And you kind of just have this like schedule, right? But instead, they have this more complicated system where they train individual policies on the get up, individual policy on the soccer, and then they train the 1v1 with this kind of more complicated regularization that tries to do behavior cloning depending on the situation that the robot is in. So this is kind of what I mean, that I feel like DeepMind is really, really advanced in these kind of curriculum, like fancy self-play curriculum strategies, because it's what they've been doing for a long time now, right? The Go systems, the chess systems, all of those are very have a very complicated and nuanced kind of schedule for these curriculums and the self-play. So they're kind of showing you that they're very good at that, and DeepMind is. Alternative approach is to train the agent against a copy of itself, right? This is the whole self-play. Uniformly, randomly sampling the opponent per episode leads to improved performance. Yeah, so this is just a fancy way of saying that, hey, rather than the agent playing exactly against itself, have it play against an earlier model checkpoint, an earlier version of itself, right? Uniformly randomly sampling just basically means choosing a random agent from previously trained policies, right? So the agent at time step 100 learns or plays against the agent at time step 90, right? Where in the time step there represents kind of the total amount of training that has been done. Yeah, you know, like, look at this. Snapshots of the agent's policies are regularly saved. Another way of saying that is checkpoints of the agent's neural network are regularly saved. But because this is a reinforcement learning paper, they use all the reinforcement learning terminology, but underneath it's really the same exact thing that you're doing with machine learning and models and checkpointing, except now it's called snapshotting and it's called agent policies instead of just a neural net. Blah, blah, blah. The performance of the opponent improves over time, but does not catch up too quickly to that of the agent. Playing against a mixture of opponents. Blah, blah, blah. Sim to real transfer. Okay. Our approach relies on zero-shot transfer of trained policies. So they basically took the policies that they learned in simulation, just applied them directly onto the real robot, and it just works. And that's really impressive. And how the fuck did they do that? Well, they did that with domain randomization and perturbations, which is just basically a form of domain randomization during training. So in simulation, the robot is constantly changing, right? So here are a bunch of different numbers here. You have like friction, you have the maximum torque, you have maybe proportional gain, you have damping, you have armature, whatever the fuck these are, right? These are numbers that are hard-coded in the simulation. But what they do is they say, hey, what we're going to do is we're actually going to mess with it, right? So every time we start a new game in simulation, sometimes the friction is going to be 0.03, and sometimes it's going to be 0.02, and sometimes it's going to be 0.04, and sometimes it's going to be 0.031. So the robot is going to get very good at basically dealing with changing friction, right? So that whenever you actually put it in the real world, it's going to have no problem with it, because in the real world, the friction might be, I don't know, 0.27, and it's like, oh, no problem. I've worked in friction of 0.02 and I've worked in friction of 0.04, so I can deal with it, right? That's kind of the core concept behind domain randomization, where it's like make the simulation more varied than the real world. So we randomize the floor friction 0.05 to 1.0, varied the joints, varied the positions, attached random external masses. So sometimes the robots in simulation have like a random lump on their arm, which forces them to kind of like fall off to one side. They added random time delays to the observations, right? Make the robot's life in simulation very, very difficult. Applying random perturbations to the robot during training in simulation substantially improved the robustness of the agent, leading to better transfer to the real world. Look at this. We applied an external impulse force of 5 newtons to 15 newtons lasting for 0.05 to 0.15 seconds to a randomly selected point on the torso. So the entire time that this robot is training, it's randomly getting pushed, right? There's randomly there's just a random force at any point on the torso every 1 second to 3 seconds that's just randomly pushing it. So, that kind of explains why the robot is able to so well adapt to the human, right? So like here the human is pushing the robot. Robot doesn't care, dude. The robot literally spent its entire life in simulation getting pushed around constantly. So these little human pushes, no problem, right? Who cares? Look at that. It can survive. Oh, you want me to get up? Get up. I can get up this way. I can get up that way. I just love this little robot, dude. It's so cute. Right? We limited the range of possible actions for each joint to allow sufficient range of motion while minimizing the risk of self-collisions. We also included 2 shaping reward terms to improve sim-to-real transfer and reduce robot breakages. Highly dynamic gaits and kicks often lead to excessive stress. Right, so this is what we were talking about before, where usually you have regularization terms to reduce the speed, right? So in the simulation, the robot is penalized for having really fast motion of the joints and really aggressive torques, and that makes it less likely to break the real-world robot. Yeah, so this is the reward shaping that I was kind of talking about, how like unfortunately there's still a lot of reward shaping in these reinforcement learning systems where hey, it's not working well. Okay, well, let's add this one little extra reward term and that'll fix that, right? And then you do that over the course of a project, and then you finally get to the end of the project and you realize your reward function has like 10 terms and each of them has like a little weight in front of it, right? So these reward functions can get pretty complicated pretty quickly. So for example here, they noticed that in the simulation the agent would lean forward when walking, which was kind of a way to make it more fast, right? Like human sprinters do this, right? When you sprint in real life as a human, you tend to like lean forward. But when you try to do this in the real world, the robot falls. So what they did is they added an extra reward term that kind of says, okay, if the more you lean forward, we're going to penalize you for that negative reward for doing that. Okay, results. We trained agents to play 1-versus-1 soccer. Training the get-up and soccer teacher took 14 and 158 hours. So I'm assuming this is in simulation. So we have 14 and 158 hours of simulation, which is actually pretty fast, especially if you do that in parallel. And the self-play took 68 hours, which is also really fast. So this is actually very refreshing. I would have put an extra 0 at the end of all of these. I thought that they were going to say over 100 hours for each of the behaviors and then probably 1,000 hours for the self-play. But it actually seems like all of this was actually trained relatively quickly, which is actually even more impressive to me, right? Because this isn't like the result of 10 million GPUs burning for a month. This is actually 68 hours is pretty reasonable. Okay, so they do some ablation, blah, blah, blah. They look at the different behaviors. Here are all the different skills that kind of naturally emerged from this self-play, right? You have kicking the moving ball. You have dynamic defense, blocking a shot. You have turning, so it learned how to turn, right? At no point was it taught to turn. It just learned how to do that. Getting up from the back, getting up from the front. It learned how to position itself between the ball and the own goal. So this is one of those behaviors, right, where you're going beyond just controlling your local kind of joints, right? Now you're starting to plan in like a time space that is tens of seconds, right? Because now it's not just, okay, I need to move my leg. It's I need to move my leg such that I position myself between the ball and the goal so that I can better defend, right? So it's like these kind of, it naturally learns the more complicated game dynamics, which is, right, what happens with chess and Go is that the Go robot, or the Go agent, right, the Go neural net learns these kind of very long range, kind of like time, almost strategic planning decisions. Okay, say compare the walking speed, they compare the get up, they compare the kicking. Yeah, this is interesting. So embeddings of the joint angles recorded while executing either the scripted baseline walking policy or the learned 1v1 policy. Okay, so here you have the scripted baseline walking. So what does that mean? That means a human designed this exact walking motion, right? So this is a walking motion where you see it puts its little left foot out, then it puts its little right foot out, then it puts its little left foot out, and it repeats. And that's how it walks, right? And this is a scripted baseline, and that a human designed this. So the embedding of the joint angles, what does this mean? So joint angles, right, there's 20 joints, 20 degrees of freedom in this robot, and it has 20-dimensional joint space. So if I were to plot a trajectory in a 20-dimensional joint space, I couldn't understand that, right? As a human, I'm kind of capped out at 3 dimensions, maybe 4 dimensions. So what they say is, okay, we're going to take those 20 numbers, which represent the joints, and we're going to embed it into 2 dimensions here. So this is a 2-dimensional visualization of joint space. So each of the points here represents 20 numbers, which represents the angles of a joint, or the angles of the robot. And you see how this is a closed loop, which means that walking in the scripted baseline repeats. So you basically execute the same thing over and over and over again, right? And here on this side here, this is the learned policy. So this is all the different points whenever the robot is playing soccer. And you can see here how some of these loops also exist, right? You see how like this walking, here it is, you have the left kick, you have these like specific loops in kind of embedding space that represent higher level actions such as getting up and kicking, which is pretty cool, right? And notice how there's a lot of empty space here, right? Which is also important. What that tells you is that in the points here in joint space, or in this joint embedding space, are not actually useful, right? Almost kicking something isn't useful at all, but kicking something is very useful. So that's why there's a lot of empty space here. It's a very specific position in embedding space, in joint embedding space, that results in you actually kicking and doing something useful. So a lot of time, it's not about increasing the total kind of coverage of the joint space. It's about figuring out which specific areas of the joint space are the only ones that are useful for doing things. Skill embeddings. This is super awesome stuff. I got to work with someone who did a bunch of skill embedding stuff at Brain, and it was like really awesome. It's basically this idea of not just taking joint angles and projecting them into an embedding space, but then taking skills and projecting them into an embedding space, which views the gate as a motion through 20-dimensional joint space. Trajectories produced by a given policy describe a manifold embedded in this space. We use the uniform manifold approximation UMAP. This is a way to visualize this, kind of like a PCA, if you want to think about it, right? It's a way of reducing the dimensionality of a high-dimensional space, usually to a visualize, right? So most of the times when people use PCA or TSNE or these UMAPs, the reason they're doing that is because it's very difficult to imagine what a manifold in a 20-dimensional space looks like, but a manifold in a 2-dimensional space is much easier to visualize as a human. Show much richer structure. Yeah, there's much more interesting embedding space here. We can also see 4 topologically distinct loops, right? They're talking about these loops here, right? Here in the scripted baseline, you just have 1 loop, but here in the learned policy, you have more complicated loops. And not only are they more complicated, but they also have a more varied kind of shape, right? So this get up behavior from the back, it doesn't always start from the same place. You see how here there's a trajectory which starts from here, and then there's also a trajectory which starts from here, which means that there's different get up behaviors, right? The kind of thickness of that trajectory in embedding space is thicker than here in the baseline, where it's like it's always going from the same place to the same place. This perspective offers another way to see how the learned policy is able to fluidly bend both pre-trained skills and emergent skills. So here you have some set pieces, I guess. So these are like special little kind of environments where I guess one of the robots starts here in the corner and the other one starts here, and then basically they learn to block each other or something like that. Here they're showing you how in the sim versus the real, you're going to get slightly different results. So in the sim environment, you see how much more consistent the ball is. So you see here the ball almost always ends up in the goal. The robot is very good in simulation. It knows exactly how to kick that ball to get it exactly in the ball, in the goal, right? The shot accuracy. Versus in the real environment, because it's not actually trained at all in the real environment, it's just zero shot transferred, you can see here that that same kicking actually results in a lot more diversity of the ball location. Look how clustered the sim ball trajectory is versus the real ball trajectory. To gauge the reliability, we designed penalty kick and get up shoot set pieces implemented in simulation in the real environment. Blah, blah, blah. Set piece, sim versus real. Of course, zero shot, sim to real, you're always going to have a little bit better performance in sim, obviously because it's been trained in sim, and the simulated world is a lot more consistent. But these are pretty good, right? 90 to 70%. Like kind of, I'm used to 90%, 10%. Right? Like I'm used to like a real drop, right? An actual sim to real kind of performance drop. But here it's actually quite good. We analyze the footstep pattern. Okay, so they're counting the amount of footsteps. They're kind of like looking deeply. What do we got here? EQ versus ball ego velocity. EQ versus opponent velocity. Heat map of the critic's expected return versus the ball velocity in x, y meters per second. So the critic is a neural net that is trying to approximate the reward, right? The expected value of the discounted reward. Basically, it's trying to tell you how good is this state that I'm in, right? So if I'm close to the ball and I'm right about to kick the ball, the critic is saying, you're doing good. If I'm in the opposite corner of the field and I'm not looking at the ball at all, the critic is going to tell you, you are not doing good, right? So the critic is a neural net that tries to tell you how good you're doing, and the policy is the neural net that actually does the thing. So what they're trying to show here is that when the ball is either traveling toward the goal or remaining near the agent, you get a high value. So a high, here the critic is telling you you're doing a good job, and here the critic is telling you you're doing a bad job. And here for some reason they flipped the fucking colors. I don't know why they would do that, but here is you're doing a bad job and you're doing a good job. So you can see here, whenever you're close to the ball and whenever the ball is moving, I guess, in this direction, which is towards the goal, you're going to get a high. Critic is saying you're doing good. But in this case, you're doing bad. The predicted value is lower when the opponent is located between the ball and the target goal. Observation coordinates fixed in text. Here you have kind of the little trajectories. Here they do some ablations. Self-play versus untrained, self-play versus untrained teacher, self-play versus untrained teacher 1v1. I mean, these are pretty noisy, so it's hard to really get anything out of that. Sparse reward. So sparse reward is kind of a way of saying that there's no reward shaping or this kind of reward engineering or reward design, you know, like it's not like a complicated shaped reward. It's just sometimes what they call it when you have these complicated reward functions. So a sparse reward is just you get a score of 1 for doing the thing and you get a score of 0 if you don't do the thing. And it just makes it a lot more difficult to learn the actual task. Without self-play. We investigate the importance of using self-play. And finally, at the very end here, we get a related work section where they're just going to reference every single other DeepMind paper so that they get a bunch of citations and that they continue to get funding. Because unfortunately, the way that academia works, right, is you get grants, and in order to get those grants, you have to show that you have a high number of citations, which means that people are looking at your papers that you're publishing and using them, which means that there's a huge incentive for people who publish papers to cite all their previous work and all the previous work of all their friends so that they can all continue to get citations. So, unfortunately, when you read these related works sections, they can be very biased in the sense that they will only tend to cite their own work and try to ignore the work of people that are competitive with them. So maybe there's another lab somewhere else that also does robots and soccer, but you won't see any citations to that. And it's kind of annoying because, you know, you can have almost these kind of like siloed research efforts when really they would benefit from kind of joining together because of just kind of the incentives of citation and kind of the way that grants are given and so on. Yeah, transfer knowledge from the teacher to the student via a distillation loss or KL divergence between the output of the student and teacher networks. I feel like there's something better than KL divergence. I don't know what it is, but like my intuition is telling me that there's something. Love these streams. Are you interested in covering the new open source RLHF models like Open Assistant or Stable Vicuña? I do have streams on those, Lamb. So I did a stream on Open Assistant where I played around with it, and I don't know if I did a stream on Stable Vicuña, but I did do a stream on Llama. So you should go and check those out. If you have any new papers that are in the RLHF world or LLM or NLP world, feel free to drop on the Discord. There's a link in the description. We have a little community there, and you can post papers, and I will try to read those papers. Multi-agent reinforcement learning. RoboCup. Yeah, RoboCup is pretty cool. RoboCup has been going on for a long time. This is different. So RoboCup is like these little, like almost like Roomba looking robots. RoboCup. But these guys have been doing it for a very long time. RoboCup soccer. Yeah, they have the little humanoid ones, but the real competitive, it looks like this. So I've gotten to see some of this. I remember I was in Japan for a conference, and then they had the RoboCup there. And these robots are very fucking good. Like, especially the little ones, these ones. So there's different leagues. They have a humanoid league. They have like a big league. These are like the big ones. And then they have these like little ones that look like this. These little ones are like crazy. Like they go so fast. Like it's almost like you can't even, you don't need, you have a hard time understanding what's going on as a human. because the game just is so quick, the pace of the game. Like they zoom around really quickly and they just like shoot the balls, and they have all these extremely complicated strategies that they do. So RoboCop, definitely cool. Definitely check it out if you're into robots and kind of competitive robotics. System defines fewer skills, blah, blah, blah. Competitive games. 1950s. What is a use of artificial intelligence in a 1950s game? I don't know if I've ever seen that. What the fuck are they talking about there? Limitations. Our work provides a step towards practical use of deep reinforcement learning for agile control of humanoid robots in a dynamic multi-agent setting. However, there are several limitations our work does not cover. Low-level behaviors necessarily compromise between stability and dynamism. We could potentially obtain behaviors that improve in both aspects by using insights from multi-objective RL. We do not leverage real data for transfer. Yeah, everything is done in simulation, but I feel like that's actually a better way to do it. Fine-tuning on real robots or mixing in real data during training could help improve transfer and enable an even wider spectrum of stable behaviors. Maybe not. You know, I feel like sim to real has some benefits to it in that you don't need to do any real training. Could lead to more human-like behavior and improved perturbance rejection and safety. We applied our method to a small robot and did not consider additional challenges that would be associated with a larger form factor. Comparison to RoboCop. All right. Inspiration for our 1v1 is RoboCop, where the OP3 has been used for the Humanoid League. However, our environment and tasks are substantially simpler than the full RoboCop problem. Right? In RoboCop, you have a whole team, and they have to play together. But I would say the control that you're using here, this kind of like end-to-end reinforcement learning-based control, is significantly more impressive than the Humanoid League in the RoboCop. The Humanoid League in the RoboCop looks extremely clunky. They're all just kind of like shuffling towards the ball, and then they like try to kick it, and like half the time they're falling over. It's really not as impressive as this stuff here, and it's kind of a fundamentally different type of robotics. This is where I feel like they really missed out. The raw vision. Everything in this paper relies on the motion capture system, right? It's almost like the cameras are worthless. They're not using the cameras at all. At first, we investigated how to train vision-based agents that only use onboard RGB. Learning from visual information requires overcoming additional challenges. Yeah, it's just a significantly harder problem. Makes the problem significantly harder. So I think they tried, but they couldn't do it, and then they ended up not doing it. In order to bridge this gap, we created a visual rendering of our lab using a neural radiance field model. Okay, that's pretty cool. They tried to use a nerf. We randomized training across multiple collected nerves to improve the agent's real-world performance. Damn, they actually tried. That's actually quite impressive. They used a nerf, and then they had domain randomization within the nerf. Damn, this is actually pretty good. 60% on the kick? I don't know why they didn't show that. That seems like it would have been way cooler. Provide an additional indication for the ability to solve soccer from vision. Oh, this is simulated vision, though. They didn't actually tell you what the real one was. Conclusion. We applied Deep RL to low-cost humanoid robots and taught them to play 1v1 soccer. We trained an agent in simulation in 2 stages. In the first stage, we trained 2 independent skills, one for getting up and a second for scoring in the presence of a random opponent. In the second stage, we distilled the skills into a single soccer agent and improved its game tactics via a form of self-play. Playing against an earlier version of itself. We found simple system identification and light domain randomization, combined with relatively strong random force perturbations to result in a surprisingly effective transfer. The agent learned dynamic skills that are beyond what one would intuitively expect. The motions are dynamic, and in experiments, the emergent behaviors exceed the performance of corresponding baseline controllers. Even though the learned policies could be improved in terms of stability and perception, our results are encouraging, and we believe that similar methods could be applied to a larger robot to solve practical real-world tasks. Pretty cool. Let's see, is there anything interesting in the appendices? What do we got? Joint limits. So these are each of the 20 joints, right? Head pan, head tilt, and then this is the radians for the min and max. So basically how far do each of the joints turn? Distributional MPO, this is the specific type of RL algorithm that they used. The Q function is the critic, right? This is the neural network that tries to approximate the value of a given state in action. And then you have the policy, aka the actor, aka the neural net that actually outputs the action. Or usually the mean and the variance of a distribution, which is used to then get the action. Here you have your standard reinforcement learning objective, right? Maximizing the Q, where the Q is the value that you're getting from the critic. Here you have a temperature. Solution to the convex dual function. Rather than setting the temperature to the exact solution, it is effective to optimize the temperature, initializing with the solution found. A lot of hyperparameters. And unfortunately, they're probably all just hand-picked. Right, here's your discount factor, 0.99. Guessed it correctly. These are really small little networks, right? So look at this. The critic is only a fully connected multi-layer perceptron, 400, 400, 400, 300. So that's really small. The policy also very small, right? It's just literally 3 layers, 256, 256, 128. So that's another thing to note here, is that in these reinforcement learning papers, the policy networks, which are the policy, which is parameterized by a neural network, and the Q or Q function or critic, which is parameterized by neural networks, these are very small neural networks, right? This is not a billion parameter or like 400 million parameter neural net. These are like literally tiny neural nets. You got some layer norms, of course, to use LU activations. Got some atom, batch size of 256. This is the stuff that, you know, would have been really awesome if they did it entirely from vision, but of course it just makes the problem like 100 times harder, so I think we have to wait another 5 years before we see this exact demo, but done entirely from vision. And that's it. All right, guys, we made it all the way to from the top to the bottom. 34 pages of deep reinforcement learning to solve this little soccer task, you know? This was pretty cool. I just love this video. Just how cute is this little robot? Look at it. Look at it. It just wants to get to this little ball, and like she keeps pushing it, and it just like doesn't give a fuck. Little robot keeps going. Look at it go. Oh, get it? Left shot. Boom. And I just love how this little robot here is just sitting there in little T pose. So adorable. All right. We're going to end it there. Thanks for watching. Feel free to drop on the Discord and join our little community, and you can help recommend papers, and you can help pick what we read. So yeah, thanks for watching, and see you guys later.